Good day, everybody. This is Maciej Hruszowski of Red Hat Research, and I would like to welcome you to our June Research Days event. Our main speaker for today is Freya Alfredsson, a PhD student at Karlstad University in Sweden. Together with Frey, let me welcome Toki Hoyland Jorgensen, a principal engineer at Red Hat, who has taken the role of conversation lead. Gentlemen, welcome, and please take it away.
Thank you.
Thank you. So should I jump right into the slides?
Please do.
Thank you. Well, thanks for the introduction, Mate. So like Mate said, my name is Frey Alfredsson. I'm from Karlstad University. And in this lecture, I would like to introduce you to my PhD work that I'm doing in combination with Toke and Jesper from Red Hat. Now, because I know this is a mixed crowd, some people are used to XDP and others might be new to BPF. I'm going to start by going through a little bit of a background of what BPF is. You can also ask questions while I'm doing the lecture. Toke will stop me in between and I'll ask questions to see if there's somebody with a question to me during the lecture as well. Now, what is BPF? So the BPF environment is a runtime environment that allows us to run code within the kernel, in kernel space. I like using the Java virtual machine as an example because most people here are familiar with Java. So you could think of it as the same concept. You have a in-kernel virtual machine that is capable of running programs within the kernel. Now, this is a full ecosystem. It has a full toolchain of compilers, loader libraries, and tools. So quite a mature system and not just a virtual machine within the kernel. And one of the differences that we can immediately spot is when we're using normal applications within the user space, we usually have a CPU that's provides a sandbox on runtime. Make sure that we are within user space and can't run kernel commands. However, with BPF programs, we have to load the programs into the kernel using a system call, which will then within the kernel run a verification process that will create a sandbox around the application. This basically means checking if they simulate the potential amount of commands or as instructions the application can run, that it doesn't exceed 1 million instructions. This makes sure that the application doesn't have infinite loops, that it doesn't use any helper functions except for this particular type of BPF application. You can see similar to system calls, we have something called BPF helper functions. And that the application doesn't reference memory that it's not allowed to use. Now, what are BPF applications? These are technically hooks within the kernel. We actually have probably far beyond 100,000 hooks within the Linux kernel where we can hook in different types of BPF programs. These come with all sorts of types. So for instance here, and if you notice the B here, this is called the EB. Every time you see either eBPF or BPF, it's the same thing. And when you see the EB, this is a particular hook that we can run a BPF application. So on all the other slides, you will see those here. So here we could run applications that are either monitoring every system call that's being run, or the virtual file system, or even the I/O of a block device, or anywhere pretty much in the networking. And what I'm working with is XDP, and that means not only can we just monitor, we can even modify or even affect the process. For instance, when it comes to the networking part. There are all types of eBPF hooks. You can even monitor user space, and some networking devices even have the capability of running BPF code on the networking devices themselves. And I think one of the best ways we can get into what BPF is just running an example. First, I just want to mention here, like I said, depending on where you're running within the kernel, like which hook you're running, there are different helper functions involved. The sandbox makes sure that you can only use the helper function for that particular BPF hook, and that you can only access the memory that this hook is allowed to use. So just as a small example, because I think for most people, they can see an immediate gain by looking at something like the BCC tools. There's also binary tools, like if you install the BCC package on pretty much any Linux distro today, you'll get these tools. There's also something called libbpf tools, at least on Red Hat-based systems, which also gives you more applications. And my favorite applications are actually these bio latency and bio tools, but for some reason, my this particular Fedora version, those are not working on that one. But I'll show you a few other examples, such as here I'm running an application that is monitoring system calls. And after a bit, I can stop the program and it'll show me how many times particular system calls have been called. Or something called OpenSnoop. It will show all files and which files are being opened by different applications. And I can show one more. If I do here, this is BPF. This is the binary version, not part of the BCC tools, I think. I think it's the bio latency here. So this one at least works of the bio tools. So I have an NVMe device and a normal spinning disk. So now we can get like a graph that shows, for instance, what the latency is in microseconds of the different IOs that have been happening on my device. So you can sort of see immediate benefits of running these on your own computer. Okay, so if we go on, BPF offers inter-process communication using these so-called BPF maps. Well, these are just memory maps that are predefined within the environment. And if I show you here in the console, if you do man BPF, it's actually quite a good man page. And go down to here, let's see. I think I'll just do map, must be here. There's a list of different types of map types. So when you create a BPF application, you can create these different maps, which are loaded into the kernel memory. And that could be a hash map, or just an array, or even a pair CPU hash map for added speed, and pair CPU array, and so forth. So you have quite a few different types of maps that you can use in your application. But what you can do here is then do user space to kernel space inter-process communication, as in the user space application can write or read from these maps, depending on the type. And then you can have the BPF applications read and write to these same maps. Otherwise, this is like the only way you communicate with between these processes. So now you have a way of monitoring things or doing things in the kernel. The one thing to keep in mind here, what are you actually getting from using these BPF application rather than the alternative? One is you're getting quite safe domain-specific code that you're running in the kernel without worrying about making a kernel module that might have serious bugs or access to too many things. And by using these maps, like if we trace, for instance, the top application, you'll see that this is monitoring all sorts of different applications using the proc file system. And it's a lot of system calls. Instead, a BPF application can run within the kernel, collect information, which the BPF application then just reads once in a while instead of having to read individually from all of these different locations from user space. So it's quite efficient to have these BPF programs.
We have a question in the chat here.
Yes.
If I'm interpreting it correctly, how are new map types added to BPF? If you want a specific data structure in your program, how would you go about doing that?
So these BPF data types are just part of the kernel. So you would have to go through the basically through the kernel community and submit a new map type. So hopefully the map types that are already there will suit your needs.
I think you may be coming back to this later as well, right?
Yeah, I think so. It's because we actually add a new map type. So yeah, okay. Yes, so I hope that answered the question, but we'll come back to it in a moment. Okay, so what type of applications can we expect from BPF? Like these applications that I've been showing are very easy. Like I said, just monitor something specific or do something very simple. But if we look at the options, we could create, for instance, security-wise, an intrusion prevention system, something that monitors system calls and then even blocks the network or changes the behavior of the application depending on what has happened. For debugging and tracing, a very nice facility here is that we can not only just debug the applications we're trying to figure out what's wrong with, we can even see how it's working with the kernel itself and actually figure out if there's a bug related to the kernel or something that's slowing it down within the kernel. If you're a system administrator, you might be looking into performance issues, or you might have a production system that you're replacing with new hardware, and you can monitor then the I/O patterns and figure out, okay, which RAID size do I need for the new production server? So it opens up quite a lot of possibilities. Then, of course, monitoring, which is like we just saw, we could add pretty much anywhere, even in the process scheduler, to see how often or how long and so forth the process are scheduling. You can even attach BPF programs to BPF programs to monitor BPF programs. So it's you can pretty much attach to everything. You can also attach, if it's compiled into the kernel, to all functions within the kernel, if you just want to monitor a specific function. There is a very nice tool here called BPF Trace. Now, BPF Trace is an application that's very similar to the awk application. So like if you're familiar with awk, for instance, here's a small application that just reads the etc passvd and prints out the user names and their user IDs. BPF Trace is very similar. I can give you an example here. I'm going to clear my screen. Here you can actually add directly in trace points or some hook that you want to attach a program and write the program directly into this BPF trace program. And this is a very similar program to check which files are being opened. So it's just printing out the name of the program and the parameter to it. So this might also be a nice place for you to just try things out with this easy to use BPF trace program. Another thing I want to show you here is with BPF trace, you can also list all the particular hook points. There are actually more than these, but if I count them here, you can see that at least on my machine, I have more than 118,000 hook points that I can actually monitor within my kernel at the moment. And then there's networking, and this is what my PhD is all about. It's BPF in relation to networking. And networking we can create with the technology that I will explain in depth in a moment. Acceleration, load balancers, DDoS prevention systems, and more. So it will be apparent what we can do in just a moment. Is there any questions at this point with BPF? Nope.
I don't think we've had anyone asking any more questions in the chat.
Yes, no problem. Then I'll just keep going. So let's go through the BPF lifecycle. How do we develop these programs? I've shown you how you use BPF trace, which just runs them pretty much directly. But basically, we write a program traditionally in C. It can be any programming language that can create BPF bytecode. And then we compile it into bytecode. Today, it's very popular to use Clang. I know GCC is adding BPF support as well. Then within this bytecode, you have program sections and maps defined in the bytecode. And then you use through your application, user space application written, preferably a library like libbpf to do all the heavy lifting for you, to load the application into memory, that is getting it through the verifier. If you write an application, like a BPF application, it's going to take a while for you to get used to the verifier. It's most of the issues that I have is just trying to figure out why the verifier is stopping me. But on CPUs that it supports it also jits this BPF code into the native instruction set for added speed. But the libbpf library, apart from just loading in the BPF program, it also adds these maps into the memory and attaches them to the places where you want them to be placed within the kernel. Okay, so this is the full BPF environment. Just as a side note, if you're looking into just the code and you want to check out like a few different programs, there are 2 different places I can recommend, or actually 3 here. One is the IOVisor project, BCC. This is a loader library in Python, which most people recommend moving away from. But they do have libbpf tools, which is like all these tools rewritten in C. So here you can see these different applications. I can find here the syscount, the one that was counting the number of system calls that we had called. And you'll see that the user space application is called syscount.c, while the BPF code just has the .bpf in the name. So these are quite simple to follow examples of BPF programs. And you'll see here, like if I go into the BPF code, here's the definitions of the different maps. Like here we can see it's a BPF hash map with 64-bit values and a key that's 32-bit, and another hash map here. And then finally, we can see the actual hooks themselves, and they're defined using these sections. So the name within the section defines where it will be hooked into the kernel. You can see that these stubs are quite easy to write. Here's just getting like the process ID and some time using a BPF helper function, and then finally updating the map here. So this is quite easy to follow code. We also have at the XDP project something called BPF examples. We have different types of examples that you might want to check out as well, depending on your use case. There's also something called the XDP tutorial, which is very nice. It's only about this one type of hook called XDP, which I'll go through in a moment. And I really recommend going through this one, even if you're interested in just making other types of BPF applications, because this is one of the better tutorials you can find online. Okay. So now that I've introduced you to BPF and shown you some examples of what you can accomplish with BPF and even where you can start if you're not even into networking, I'm going to go into a little bit of background for what we are going to go through in my work. I'm going to start with packet scheduling. So here I've put together like a very simple example of a round-robin packet scheduler where the individual packages we can see here are numbered depending on their flow. So a flow is just a way where we have enumerated packages into a group. So this might be anything from just packages that belong to a specific VLAN, or it might be IP address based, enumerated from IP addresses, port numbers, protocols, or even a combination of all of them. So it might be like a production environment or 3 different clients and their traffic. But basically, the traffic that comes into the scheduler is unordered, but the scheduler will then queue in 3 different types of queues depending on the flow. So we have them organized after flow, and then just dequeue 1 packet at a time in a round-robin fashion. And you'll see they will all be organized then after that, giving all the different users equal traffic. So this is basically what packet scheduling is. That you have the capability of being able to rearrange the order of the packets. Now, so I can tell you a little bit why would we want this? Well, a very easy example would be this, just like we talked about, having every client getting equal share. It could also be that you just wanted to give a production environment a priority over the testing environment, if you have virtual machines or any type of environment in that sense. Or, which I find more interesting, like for you at home, prioritize sparse flows. So basically, like we all at home might have multiple people using the network. Some of them are playing video games, others might be streaming, or others might be using messaging applications. Now, we don't want heavy downloads or heavy streams to affect gaming or these applications that are more time sensitive. So having a scheduler that tries to prioritize sparse flows, or those that aren't sending a lot of packages, immediately gives you gain with your router at home. Another thing with queue management, or even active queue management, would be to mitigate buffer bloat, which is also very interesting, especially for people at home. So we do have a big issue in all of the internet today, where networking equipment suffers from buffer bloat. Basically, that the queues tend to be too long or too big, and we end up queuing up too many packages and getting more latency. That's an oversimplification, but I think my favorite way of trying to at least get some feeling on what buffer bloat is, if you're pouring water into your kitchen sink, and let's imagine the water is packages, but we've all been there. If we pour directly into the drain and the water goes directly through the drain, then obviously we're getting rid of the water very quickly and there's no issues. But if you hit the side or you overflow the drain and you have a little bit of water spilled outside, have you ever been in the situation where you're pouring water and there's equal amount of water going out of the drain of the sink as you're pouring into it, and there's just like an equilibrium? That is basically buffer bloat. So ideally, the packages would go directly through without buffering up, but because they're buffering up, you're getting unnecessary delay, even though there's equal amount of packets going in and out. But I recommend checking out the bufferbloat.net homepage for more information if you're interested in that. They even have solutions that you can set up with open source at home to make your internet better. So it's quite a difference. Okay, so now that I hope I sold you that packet schedulers and queue management is actually something we want, not just an extra feature, let me introduce you to what Express Data Path is. So Express Data Path is just a BPF hook within the kernel, or more specifically within the drivers of the network cards, or the network card drivers. And it allows us to process or run the hook on each packet that comes into the kernel right after a DMA transfer, and therefore directly before it actually goes into the network stack, or even you could say into the kernel. And this particular hook gives us very interesting capabilities, such as the capability of manipulating the packet. You can change the contents, everything from maybe replacing the IP addresses, or if you want to add or even subtract a VLAN tag. You could redirect the packages, and this is basically, I would say, one of the best features. You could either redirect the packet directly to another network card, or reflect it directly out the network card, bypassing the kernel completely. And we want that in some cases where we have high-speed network cards, or we don't want to go through all the network stack. So keep in mind, today we're getting network cards that are maybe 100 gigabit, which gives us just like 27 nanoseconds to do anything with every packet. So trying to shave off a little bit of extra latency is very beneficial. And while the network stack in the kernel is very mature and very fantastic, being able to bypass the network stack actually gives us more and better latency. Better, not more. Another feature we can do is just drop packages and obviously just monitor. So we could monitor by writing into these BPF maps information about the traffic. However, one of the problems here is that XDP lacks packet scheduling capabilities and doesn't have any queuing support. So this is what I'm trying to fix with Red Hat. So if you go through the Linux kernel, there is this queuing discipline in the subsystem, which handles scheduling and queuing support. But notice that if we want to use that, we do have to go through the kernel, which is not giving us then this flexibility of added performance by bypassing it. So another simulation to show the issue of not having any queuing support is this test that we set up, where we have a 100 gigabit network interface, which is sending traffic to a 10 gigabit interface. So there's an obvious difference in capacity. We increase the propagation delay to simulate a longer distance. And because of the sliding window and congestion prevention algorithm, TCP, for instance, tries to figure out how many packets it can send simultaneously, and tries to then tries to find a balance in that with the congestion prevention control. However, because XDP doesn't have a queue, it actually just has a little over a couple of dozen, a queue of a little under a couple of dozen, which is more like a side product of its design rather than an actual queue. The TCP protocol overflows this queue constantly, and then ends up not giving us the performance we can get if we go through the kernel. So here you can even see the outline of like the sawtooth pattern that we know from the TCP connection. So we do need if you don't want scheduling capabilities, at least we need queuing support in XDP. So what have we? How do we want to solve this, and how are we solving this? So we've provided a new DQ hook, which I've added here to the network interface as well. So now we have not just a XDP hook which enqueues a packet, we also have a dequeuing hook which is responsible for dequeuing packets. And then we've added a new BPF map type, which is responsible for data scheduling or packet scheduling. So this is where the question came in here. How do we add a new data type? We are adding a new BPF map, which is called a PIFO, which I'll introduce in a moment. But like I said, this needs to be added to the Linux kernel. So it's not as easy as adding a BPF program to a hook. Okay. Any questions so far?
Yes, we have a couple of questions.
Okay. Maybe I'll go back here then.
So the first one is there's a couple about XDP in general. I think we'll go with those first. So one is, how much delay is added by just turning on XDP and using it for monitoring, assuming you still send the packets on through the kernel stack, but just the additional delay added by XDP itself.
Yeah, so these XDP programs are quite small, actually, and they don't cost anything until you turn them on. And I'm not completely sure how much they cost when they run, but I know that they're, especially if you're just monitoring things, they don't cost much. Maybe, Toke, you have a number there.
Yeah, so the overhead of just calling a BPF program in general is, because it's all jittered into native machine code, it's basically on the order of a single function call, which is a few nanoseconds. And then, of course, the runtime of the BPF program itself can be large if it's a really large program, but it's I don't have any hard numbers for measuring the actual latency, but it's on the order of a few microseconds at most, just for turning it on if you're not doing anything with it. There's some other effects of turning it on where, depending on the hardware, you may sort of reconfigure the NIC, which can have some effects, but in general, XDP is designed to be very low overhead just for running it. Okay, so another question related to XDP in general from Arthur Navarro. So he says, not sure of what NICs do before DMA, but is there a heterogeneous amount of smartness among NICs that make it hard to predict what processing has already been performed before DMA? And if so, does it leak to the hooks we might develop, or is it handled by the driver?
Wouldn't I actually have to say this is something that I'm not 100% sure of, but I know that some settings can have effect, but like I think it's better that you maybe take over this one as well.
Yeah, so XDP runs as the first thing that happens after the packet comes into the kernel, and it doesn't really care what has been done before that. So we sort of leave that out of scope. We do have some work to integrate with smart NICs, which Jesper just added in the chat. So right now, the smart NIC is invisible to XDP. Some processing has been happened. You can't really access it other than by seeing the packet might have been changed. But there's upstream work going on, which Jesper is working on, to allow metadata, which will allow the driver, or in the future even the hardware in a smart NIC, to populate a metadata area in front of the packet with arbitrary data, where you can take advantage of any processing done on a smart NIC. And also because the smart NIC field is quite diverse, I don't think the approach we're taking is we will integrate with whatever is there. So we are trying to build a sort of flexible metadata transfer format rather than a than something where you have, for example, to offload XDP into the NIC, because some NICs do that, some NICs do other things that are still various amounts of smart. So right now we're just focusing on having a way to actually take advantage of the data. Or any processing that's done on the smart NIC. But it's all very early stages and TBD. All right, then we have a couple of questions related to actually queuing. So one is from Simone Ferlin saying, going back to the graph you had, I think, with the
here.
Yes, this one. So she says, if the queue is too short for a bandwidth delay product for TCP, the link will be underutilized, which is what we see on this graph. Could we have looked at just increasing the size of the queue to being a TCP bandwidth delay product so that this won't happen?
Well,
I think you maybe answer you. You may be answering this a bit later in your slides, actually.
Yeah, I mean, by adding this queuing data structure, we can add, we can fix this there. But like, is the question if we had not done what we're doing and just added like a queue directly to XDP, if that would have made a difference? I'm not completely sure.
Yeah.
I
Someone
think,
of you want to clarify, or shall we move on and then you can ask the question again later?
I can just say quickly. For example, if it would be possible to just increase the XDP queue that you have artificially and run your test again to see if you get close to the TCP real throughput, or you stay at this very low throughput that you had, this 2-3 gigabit.
Okay, so this goes back to, Frey, you mentioned in the beginning that XDP has a queue of a couple dozen packets. And
Yes.
I think the issue here is that that's actually a bit of a simplification. It's not really a packet queue. It's sort of a bulking mechanism that's tied to how the kernel processes packets as they come in. So we have this, it's called NAPI, which is an abbreviation of the new API, and I think it's a couple of decades old now, so it's not really that new anymore. But it's this feature where the kernel will cycle between polling for new packets and waiting for an interrupt from the hardware, which is also a way to sort of bulk up things to increase efficiency. And there's a hard limit on how much you can do this, because otherwise you will just have one CPU spinning all the time. And so the queue in XDP, what we call the queue, is actually a bulking mechanism that is flushed out every NAPI cycle. So we can't just increase it. We need to have a proper queue, which is where Frey is going on the next slide, I think.
Yeah, the queue, I actually see the hardware's transmit queue as part of the system. So we do have a queue, and you could basically try to manipulate the hardware to increase the amount of transmit capabilities in the hardware queue available, but it's really a queue that is outside of our control, and that's not something we really want. So in general, just increasing the queue is sort of what hardware vendors have been selling, but that's the wrong choice, because we have to have a smarter queue to control the queue instead of just increasing it and just, yeah, we can do high throughput, but bad latency.
and that's basically why we are implementing this PIFO map, so we can have more control and flexibility that's standardized for all XDP programs. So, yeah, I'll keep going. I want to introduce you to this new data type, this PIFO map, or BPF PIFO map. So a PIFO is just a data structure, a priority queue called a push-in first-out. It's originally comes from the hardware world, because obviously when you're dealing with the network devices that are maybe 100 gigabit, you don't have that much time to actually process the package. So one of the solutions that networking equipment has today is a programming language called P4, which allows you to basically assemble in a pipeline different ASICs to process packages at line rate. And from the research literature that we're basing this on, they implemented in hardware something called a PIFO. Like I said, this priority queue for hardware. So we're basically using that as a data type, and it's basically just a set of queues where you can place package depending on the priority in any order. However, you can only dequeue packages from the queue with the highest priority, meaning that if you finish all the packets from the highest priority, then it would automatically go to the next priority. However, if you keep pushing packets into the highest priority, then you can starve the packets in the other priorities. Now, the reason why this is an interesting data structure is because they have shown that you can implement quite a few scheduling algorithms only with this data structure. And it's very nice for us to provide programmers with a unified approach for making package schedulers instead of having a lot of different data types. One of the limitations is when you push packages into these FIFOs or these queues, is that after you add them to these queues, you cannot rearrange the package within or the packets within the queues themselves. So you can only add them in, and they will keep the order they arrived in. Now, because PIFOs were originally implemented for hardware, we added these extensions from a paper that adds these Eiffel extensions to the PIFO, which is more like a software optimization for PIFOs. And one of the things we get there is that we can also add other things to the PIFO because it's software and memory than just packets. So we can also add flows that might be just a reference to a FIFO or other data types, even another PIFO into a PIFO, and then we can create a hierarchy of these extended PIFO extended PIFOs, or Eiffel extended PIFOs. Another thing that we've implemented from this paper is something that has to do with increasing priority schedulers. So imagine if we have a scheduling algorithm that's going to be adding incrementally increasing priorities, but never reuses old priorities. Then one of the implementations we've added to the PIFO is that internally, when and let's imagine that this is a very big PIFO with 500 priorities or 499 priorities here from 0 to 499. And for simplicity, I just don't show all the queues between 0 and 100 and so forth. Now, if we never reuse older priorities, then at some point we can just switch internally to PIFOs. And when the next cycle happens, we just switch again, and then we get incrementally pseudo-infinite priorities. And I'm going to show here an example of how you would implement, for instance, a fair queuing algorithm using a PIFO, using this infinite priority implementation. Now, there's like a Python-like code here to show the actual algorithm for the enqueue hook, but I'll just mention the dequeue hook because it's only one operation. So here we have, again, a 500 priority queue where I ignore all the priorities between 0 and 100. And the packets that we're going to add to this are either there are multiple of 100. And here we have flows, which we're keeping track of flows and their n bytes, as in how many bytes are now part of this flow. So this is going to do fair queuing using the byte amount in the scheduling. So the first thing we do is when we add a packet, this is a 100-byte packet. We add it to the flow, and we add it to the time bytes. So we're going to look at the priority as time, but we're going to use it as time, like in bytes, technically. So here we get a 100-byte packet, and we register in the flow that it's now 100 bytes in this flow, and we add it to priority 0 because our time bytes is 0. Next, we add a 200-byte packet to flow 2, and we see that it's pushed here in 0 because we haven't incremented time yet. And now we have two flows, one with 100 bytes and another one with 200 bytes, but it's both just with one packet. The next thing we do when we add another packet is that we take either the maximum of the time bytes, which is 0, or the n bytes of the particular flow, when we use that as a priority to put in the next packet of the queue of the flow. So now we can see that the packet 2 is now in the placement 100 because the end of the first packet was 100 bytes later. And the same happens when we add the next packet. Then we have another 200 byte packet, because this packet was 200 bytes, we add the next packet here to priority 200. Now, when we dequeue, what we do is, so we take the time bytes and we set it to the priority. So we take the first packet out from the flow 1, and because it was in priority 0, time bytes doesn't change. Now, if there comes another package in, we can see that the end bytes was 200, so now we increment it to 300, and we put the next packet of the flow into the next section. So now we have effectively incremented by 100 bytes in the priority. Now we dequeue the next packet here from flow 2, and again, it was also priority 0, so time bytes doesn't increment. And now we dequeue a package from priority to 100, and therefore time bytes is incremented to 100. Notice that now we have a priority here that's never going to be used again because time bytes has moved. Therefore, when we get a new packet from flow 3, and then we can see here that end bytes is now time bytes plus 100, and we use the time bytes value to push here into the priority 100, because now this is the new beginning of time, and we say that the end bytes is incremented to time bytes instead. So here you can imagine that the more packages we add and dequeue, then the priorities are going to be infinitely increasing, and we never reuse the priorities below. So with this example, I hope I can have shown you that even just with one PIFO, we can implement something like a fair queuing algorithm. Now, if you want to make a weighted fair queuing implementation, you can easily just add a division here on the length and with a weight and keep track of those weights. Okay, so if you need more complex scheduling algorithms, then you can create a hierarchy of these PIFOs. That means, for instance, you could have in the root PIFO here, you might be following VLANs, while you have another type of scheduler below, which is following weighted fair queuing or something like that. And you can pretty much create almost any complexity scheduler for your needs with a hierarchy. Now, another thing we have not in this solution is, for instance, if we check up here with policing and shaping, well, we can do some policing with XDP. With this particular implementation that we just showed, we are not able to do shaping algorithms. So shaping algorithms just means that instead of just bursting out the packages as they arrive, we delay them and smooth out the curve. So currently, we don't have a delay mechanism. But future work, we would like to add this functionality. We want to do that by using the current BPF timer API that's been added to the kernel, or was very recently added if it's not there. And the idea is that the enqueue hook will then add packages to a PIFO, which is not active, as in the dequeue hook does not pull packages from that particular PIFO. And then it sets timers. And when the timer eBPF hooks run, they dequeue from those this inactive PIFO and adds them to an active PIFO, which the dequeue hook then pulls from. And therefore, we're able to implement shaping with this current API in the future with this design. Now, in summary of the work that we're doing, we want to add package queuing and programmable scheduling to XDP. We've done that with adding a new PIFO data map to the BPF map, and by adding a dequeue hook to the XDP framework. And in the future, we want to add shaping capabilities. At this point, we have these particular functions, but we are not in the stage yet to have performance benchmarks, which we hope to be able to do soon. As a summary here, you can find the new the code for the XDP DQ hook and PIFO and this particular link. And I've created a testing framework which uses Lua to test my individual PIFO schedulers that I've written. And you can find them here under the BPF examples project. And the papers that we rely on for both the PIFO and the Eiffel extensions, you can find here. So that concludes my talk. Are there any questions?
We already have an excellent question in the chat from Dave Tucker.
Okay.
Have you looked at how feasible it is to implement something like FQ-Cuddle with this architecture?
Yes, that's an excellent question. So I'm actually implementing FQ-Cuddle. I haven't can't say that I've finished the implementation, but that's one of the things that we are working on. So if we look at the fair queuing here, one thing that we can do with the FQ-Cuddle is, for instance, for sparse flows, is just to one idea is to take sparse flows and schedule them just one priority less than with this particular fair queuing algorithm. But otherwise, yes, we are working on FQ-Cuddle, and we just have a few small rough edges that we need to figure out how to solve if we want to use this particular algorithm. For instance, how it drops packages as for the cuddle algorithm, for instance, and we would like to use that as one of our benchmarks to see how the XDP FQ-Cuddle compares to the QDisk FQ-Cuddle.
Yeah, so I can add a little bit to this on the sort of API side. So this whole the choice of doing this PIFO as the primary data structure to implement all these queuing algorithms is something we took from the literature, because this has appeared as a relatively new thing, and the nice thing about PIFOs is they are possible to implement officially in hardware queues as well. So, but they are also, from the software side, they are sort of a departure from how, for example, the QDisk layer looks, where like queues are easy to do in software, right? They're just linked lists of pointers to packets, so we can shuffle them around however we want. But seeing as this data structure appeared and looks to be like the literature indicates that it's powerful enough to implement all the algorithms we want, we sort of decided to start with this and see where it goes. So there's a parallel effort on the upstream mailing list, also implementing a BPF QDisk, where you can use BPF to program new queuing algorithms at the QDisk layer, and we're hoping that we can make all these converge. I'll also add the caveat that we haven't posted any of this code upstream yet, so we haven't gotten any feedback on the kernel side. We're hoping to do that soon. So like things will probably change quite a bit before they settle, but definitely implementing the existing QDisk algorithms, showing that this can be done, has been a major focus of actually stress testing the API and seeing if it's possible. They probably won't look exactly the same, but we want to have the same packet level behavior on this, and that's still ongoing. And also going back to the other question Simone asked earlier about just having a long FIFO queue. Yes, we also want to do that, because that's sort of the minimum work we can do. So performance testing is obviously also important for XDP. So we're definitely going to do an experiment where we just use this API and do a really a PIFO that's really just a FIFO, and do a long BDP sized queue and see if this helps and what the overhead of all this is. So there's a lot of these sort of validation things that we want to do before this settles. Yes. And also in general, feel free everyone to just press the red button in the corner and turn on your own camera and ask questions. All right, we have more questions. Yeah, so I'll jump to Heidi's first. Heidi Dempsey is asking, do we plan to do any testing in a test bed that includes edge networks?
I think
edge networks here being networks that are close to. Oh, maybe Heidi will jump in and try.
Hi. Yeah, I'll clarify and also explain why I'm asking. So we have a collaboration with universities who are running 5G test beds and 6G test beds. And some of the protocols, would be very interesting in that kind of a test bed. And so I was curious about, I know you're just working out the basics of how to do it at all, but wondering whether it makes sense to kind of encourage them to connect with you.
Yes. So at my university, we do talk about 5G technologies quite a lot, and I've seen quite a lot of overlap. So at some point, I would be interested to seeing it, but
Not yet.
at the moment, we just want it working and to do performance tests on our current test beds.
Yeah.
So, but that would
we
be
can
definitely
speculate about the great future.
Yes.
Yeah, I think in general the edge is a place where you can consume this technology once it's settled a little bit, right? So the benchmarks we're doing on a completely synthetic test bed in a lab, but one of the edge is definitely a place where queuing is important, because the edge is often where bottlenecks occur, and especially so that the graph that Frey showed here in the beginning with a rate transition, right, where you have the example we used was 100 gigabit going to 10 gigabits, but the same, you still get an order of magnitude if you go from 10 gigabit to 1 gigabit, right? And if you have a data center near the edge where everything inside that edge node or data center runs at 10 gigabits, and then you have traffic going out to consumers, there will be rate transitions in that path, and this is where something like this XDP queuing can be applicable. And I think there's some interest in general. I think we're starting to see some interest in general from the telco space around using XDP and BPF to implement some of the network functionality that they have, because I think that industry was an early adopter of DPDK, which is like the kernel bypass solution, and now they've sort of realized that the Linux networking stack is actually pretty mature and has a lot of functionality that they want to integrate with, and that's really hard to do with DPDK. And that's one of the sort of general selling points of XDP in general, is that you can do acceleration, and you can do, I like to think of XDP as a software fastpath, right? So you can pick out on an individual packet level, okay, this is a flow that I want to accelerate, and I will do something with that. And all the edge cases, all the weird stuff, I will let the Linux kernel handle, and you can do this completely transparent. And I think the NFV people are starting to realize that this is actually a pretty good thing to have, because the Linux kernel has decades of battle testing its networking stack, and it handles all kinds of weird protocols, right? So if you can just take your big TCP flows and accelerate those and leave everything else to the kernel, that becomes quite compelling.
Yeah, that's very cool. Yeah, we will have at least one person coming to the September Research Days event that's live in Brno, who's an expert in that area. So we'll definitely hope to get people talking there. Thanks.
Sounds great.
Okay, moving on. We have another question from Dave Tucker. he says, I would assume that there are two classes of consumers for this feature. One is scheduling algorithm developers, and the other is standard XDP or AFXDP users who just want queuing and don't necessarily want to develop it themselves. So what is the plan to cater for the latter group of people so they don't have to implement all the algorithms themselves?
For starters, we're working on like writing algorithms and trying to put it into this BPF examples repo. So hopefully we'll just have enough algorithms that people can integrate them. Am I understanding the questions correctly?
I think so. Yes, you're going. Yes.
So if I show here my testing framework, just to if we take something simple like just the FIFO, or actually better, the weighted fair queuing algorithm, because this is the algorithm that I was showing on the slides. So this framework that I made just uses Lua, so it loads in the BPF scheduler using this syntax here. Then you create different flows, and for simplicity in this example, I just use UDP packages with different destination ports to say which is what. Create different size payloads. So these are actually now 100 and 200 bytes. And then you have these functions. One is just to enqueue a package, which basically just without going through the network device runs XDP with this particular package. And then I have a dequeue function and also one that I use with underscore compare, which just checks if I actually got this particular packet back. So it's good for debugging these schedulers as well. And here we actually have this example that I had in the slides where I'm adding the 100 byte flow, the 200 byte flow, and the second package, and then checking if I actually get these packages back in this particular order. So I'm not sure if this will be the testing framework we'll end up using in the future, but for now, this is a testing framework that exists, and I'm implementing different package schedulers here. With these PIFO maps and NQ and DQ hooks. So here we have the NQ and DQ hooks, and then the actual algorithm with this schedule packet function that I'm calling here from the XDP hook. So in that sense, like the idea is just to have a repository with plenty of these schedulers for people to be able to not have to write everything from scratch.
Yeah, and I think that there's sort of two categories of schedulers that are interesting here, right? Oh, maybe Dave, do you want to say something in relation to this?
Yeah, I was going to say, I think, this is great that the code is there and everybody can see it and you can kind of bring that into your own programs. But if you think about the way the QDIS work in the kernel today, I just say, I want that one. I don't need to go copy and paste somebody else's code that I need to watch for bugs, and I need to keep that up to date. So I'm just wondering if there's a neat way to package this, whether it becomes its own map type or whether it's as a library and we get to link that in, or whether it becomes part of the multi-protocol where you can specify that you want this particular QDISC and just have libxdp take care of that for you. I think it would be interesting to explore that.
Yes, I think that is definitely that was also what I was about to say. That there's like two different categories of scheduling algorithms. Some of the just turn them on and they do the right thing for you. FQCoddle is in that category, right? And these we definitely want to have as either a library or just a standalone application, especially for like edge network things like your home router. You should just have a magic use XDP to make my network faster command, which will load the right XDP programs to accelerate your forwarding, including doing packet scheduling and so on. And the other one is what Frey was talking about with the hierarchical schedulers, which like the main use case for that is these really elaborate policy things where you have a middle box in an ISP's network, and you have a 1,000 different customers who all pay for a particular amount of bandwidth, but you're really multiplexing them over the same 10 gig link. So you need to have some device that enforces this policy. And today people do this with the HTTP queue disk, which is really difficult to configure, but can do this. And so I think another type of application that we can enable with this BPF thing is a really efficient implementation of that, where we can like continue the research into doing higher level policy definitions and say, let's develop this policy language where you can just select the class of flows that you want and specify the policy, and we will have a middle layer that will compile this into a really efficient eBPF implementation that will do this. And I think this is one of the directions that Frey's research can continue in after we have this basic building blocks in place. So this is definitely something that can continue, and we want to make this really easy to consume. But as you well know, Dave, in general, making things easy to consume is still somewhat of a work in progress in BPF land. All right, I think we had one other question in the chat. So how would you see XDP coexisting with DPDK in these use cases of acceleration?
From my point of view, these are two different solutions. So as a coexisting, if you're using DPDK and bypassing the kernel, I mean, then you're not using XDP. So for me, I don't. If I'm understanding correctly, I find this just two different solutions to different problems.
So they can actually coexist, I will add, because there's an AFXDP. So AFXDP is is actually a kernel, is also sort of a kernel bypass thing, but it's integrated into XDP. And there's an AFXDP driver for DPDK. So you can load an XDP program, and the XDP program can pick out which packets it wants to send on to DPDK and which it wants to send out to the kernel. So I think that will be, and also here, the nice thing about this is that then you don't have to have hardware-specific drivers in DPDK. So that would be the answer to that question. But there's the glue bits, again, making this seamless is also something that we're looking into in Red Hat in general, because we do have customer requests for this. So this is still sort of early stages in making this happen. Right now, when people are doing DPDK, they just turn over the whole hardware to whichever application is doing this. And that means you really have to trust that application. Whereas XDP can function as sort of a middle layer there and do policing before the thing goes to your DPDK application.
I've no experience with AXDP. I just knew that it existed.
Yeah, and so like integrating this XDP queuing into AXDP is also something that we'll have to look at eventually. But that requires quite a bit more kernel plumbing, because there's no way to intercept package going out of AFXDP today. But we want that to be possible. And then if we have this mechanism where we can just stick packets into a map and have them stick around there for a little while, we could hook that into AFXDP as well. And then you can get nice programmable queuing from the stuff coming out of AFXDP.
Any other questions?
I think we are out of questions in the chat, unless someone want to chime in with something else. All right. I guess we can end the session here then. Thank you for the nice presentation, Frey. Thank you everyone who chimed in and asked questions, and hopefully everyone got something out of this.
Yeah, thanks for having me.
And yes, I believe there will be a recording shared at some point.
It will be directly on YouTube, right? It's...
Yes, I assume Mate has something to say about that. Yay.
Oh, yes. So in a few days, you will be able to find the recording on Red Hat community channel on YouTube, which also includes every other recording that we have from this and last year. So feel free to go there if you want to watch the other talks. And thanks everybody for coming once again.
Yes.
Thank you.
Thank you all.